In this lesson, you will see that graphs can be categorised as either Eulerian, semi-Eulerian or non-Eulerian. Later in the course, this will be used to solve route inspection problems using the Chinese Postman algorithm. First, I'd like you to pause the slide and try to draw this graph without taking your pen off the paper or repeating an edge more than once. So we're going to consider first of all, is this possible if you start at vertex A? And it turns out the answer is no, it's not possible from this starting point. There are, however, two vertices where it is possible to start at one and end at the other. Again, pause the slide if you haven't done so already and work out which vertex you are able to start at and which one you would need to end at. We're then going to consider what the difference is between these two vertices and the others. So the solution is that if we start at vertex E, there are several ways of doing this, but you would need to end at vertex F. It can also be done in reverse. We can start at F and end at vertex E. We're going to look at how these two vertices are different from the others and what it is that makes this possible. Now try the same thing with this graph, drawing it without lifting your pen from the paper and without repeating any edges. You will find for this graph it's possible to do this starting at any vertex, and you will always end at the place where you started. Pause the slide again and try to do it with this graph here. Now it turns out with this one here, it doesn't matter where you start or where you end, it's not possible to complete it without either repeating an edge or lifting your pen from the paper. We're going to look at why this is. Finally, try this one. And again with this graph, this is not possible. So we're going to look at each of these graphs in turn and determine whether or not it's possible to draw them without repeating any edges. And then we're going to look and see whether the graphs where this is possible have anything in common. So graph 1, we can see that this is possible, although we need to start and end in a different place, starting at C, ending at E. Graph 2, it's not possible to do this. Graph 3, it's also not possible. Graph 4, this is possible, and in this case we started at A and ended at F. This is possible with graph 5. And again possible with graph 6. Now you'll notice that with graph 6 we actually started and ended at the same point. We started at vertex A, so we'll look at what it is about this graph that makes that possible. So in order to understand what's going on here, we need some more definitions. So the number of edges that are attached to a particular vertex, going in or out, is either called the order or the degree of a vertex. So the order of each of the vertices in this graph, vertex A has order 2, vertex B, C, D have got order 4, and E and F have got order 3. So another definition, if a vertex has an even order, that means that the order is an even number, we would call that an even vertex. Similarly, if the order of a vertex is odd, we would call that an odd vertex. Now this is relevant in deciding whether a graph is Eulerian, semi-Eulerian or non-Eulerian, which we will look at in a minute. So pause the slide again and try to draw a vertex with 5 vertices, all of which have an even order. So you may have drawn this one. You can see that all vertices have got the same order there, all order 2. You may have drawn this one. This is K5. They've all got order 4. There are also other variations on that. Now try to draw a graph that has 5 vertices, all with odd order. So you may start trying something like this. You'll see that this almost fulfills the criteria. We've got A, B, C and D are odd, but E is even. You might then try to rectify that by removing an edge. You can see that removing an edge makes E odd, but then makes B even. You may try to do it by adding an edge. You see that this makes another even vertex at D. Now, the reason this is impossible is due to the rule a graph either has to have no odd vertices or it has to have an even number of odd vertices. This is to do with the fact that each edge has 2 ends to it, so contributes 2 towards the overall sum of the orders. And if there were an odd number of vertices that each had an odd order, then the overall sum would be an odd number. So this wouldn't be possible given that the number of edges multiplied by 2 would always be even. So graphs can be split into 3 different categories based on the order of their vertices. The first category is a graph that has no odd vertices at all, so every vertex has an even order. This is called an Eulerian graph. And a characteristic of an Eulerian graph is that it's possible to draw that graph without taking the pen off the paper, without repeating an edge, and you are always able to start and end at the same vertex. It's possible to do this starting and ending at any vertex in the graph. The second type is a graph that has exactly 1 pair of odd vertices, and all the other vertices are even. This is called a semi-Eulerian graph. And in this case, it is still possible to draw the graph without repeating any edges. However, you must start at one of the odd vertices and end at the other in order for this to happen. And the third type is a graph that has more than 1 pair of odd vertices. In this case, it is neither Eulerian or semi-Eulerian, so we would say it's non-Eulerian. And this cannot be drawn unless you repeat some of the edges. So these 3 types of graphs are going to be useful when we go on to solve route inspection problems using the Chinese postman. Let's look back at some of the graphs from the previous slide. So which of these are Eulerian, semi-Eulerian or neither? So pause the slide for a second to determine that. So you'll see the first graph has 2 odd vertices, therefore it's semi-Eulerian. The second graph has more than 2, so therefore it is neither. The third graph also has more than 2 odd vertices, so that falls into the neither category. We've got a semi-Eulerian graph for the bottom left. The next graph is semi-Eulerian as well. And the final graph, all of the vertices are even, so that will be an Eulerian graph.